Okay, well, it's a pleasure to welcome Jorge Arrieta to give the seminar this afternoon. So Jorge is a long-term friend of the Department of Mathematics here at UEA. So he first visited, I think, in 2010, the year that Spain won the World Cup. And he's come back in 2024, 2 days after Spain won the Euros. So welcome back, Jorge. He's going to speak on the flow separation mechanism in the inverse Leidenfrost equation.
Okay, thank you very much for the warm introduction, Mark. So today I'm going to present a work that I have done in collaboration with Professor Alejandro Sevilla at the Universitat Carlos III de Madrid, which is entitled On the Flow Separation Mechanism in the Inverse Leidenfrost Regime. So, well, first I'm going to explain how I organize the talk. Well, first I would make a brief introduction to the Leidenfrost effect, which I guess is familiar to all the audience here. Then I will explain the inverse Leidenfrost effect, which is the difference with the conventional Leidenfrost effect, and how this can be employed to reduce drag in a hydrodynamic drag in a solid body. What we discover when this mechanism is employed to reduce drag is that the mechanisms that or the theory that was developed to explain this drag reduction was poor. So we decided to explore or to study which are the mechanisms that really are behind this drag reduction. That I will do in section 4 and 5. And finally, I will end up with the conclusions of the presentation, of the talk. So, the Leidenfrost effect, which was discovered by Johann Gottlob Leidenfrost in 1756, is a phenomenon which we can observe normally in our daily lives. When a tiny drop falls on a hot surface, we observe that the vaporization time of this droplet is very large compared with a normal droplet lifetime. And basically what Leidenfrost did in his work, in his seminal work, was to describe this phenomenon. I have here selected one of the sentences or one paragraph where he describes that this water globule, the droplet, will lie quiet and without any visible motion, without any bubbling, very clear, like a crystalline globe. Adhering nowhere to the spoon. So this is basically due to a thin vapor layer which is formed below the droplet that is able to reduce the rate of vaporization. This is roughly, it's a very brief explanation. And here what I'm showing a droplet of water on a silicon surface in a work published by Analo Fiancé, Christophe Canet, and David Guérin in 2003. And as I said before, one of the most relevant features of these Leidenfrost drops is that the droplet lifetime is very large compared to a normal lifetime of a droplet vaporizing. But this phenomenon or this Leidenfrost effect is not valid or doesn't work for all the temperatures of the surface. And here we can see there is like a threshold. Beyond that, we observe these large droplet lifetimes for water, and whereas below this temperature, the droplet lifetime is smaller compared to the one that we observed above this threshold. So, one of the key aspects of the key features of this Leidenfrost to have the Leidenfrost effect is the temperature of the surface. I'm explaining this because in the inverse Leidenfrost effect it happens the same. So I think it's a good motivation or to emphasize the importance of the surface, the temperature of the surface. And here in this recent work published by Dana Harvey and co-workers, it was observed that Leidenfrost drops are sustained or can exist when the temperature of the surface is decreased below what is called the Leidenfrost temperature. Initially, the temperature has to be high enough to levitate the drop, but afterwards, even when the temperature decreases below the Leidenfrost temperature, the droplet is still stable. There has been a lot of research about the Leidenfrost drops, Leidenfrost droplets, not only in stagnant situations or steady situations, but also this effect can be employed to self-propel droplets. Here, in this case, the surface has ratchets, and when the droplets fall, the droplet deforms, and also the gas layer is deformed, and that results in a net force that moves the droplet towards the right. Even when the surface is flat, sometimes what happens in a recent can be that there is an internal circulation of the liquid within the droplet, and this results in a motion, in the motion or the rotation of the droplet that can be self-propelled. So what I want to recall is that still many phenomena related with the Leidenfrost effect is far from being understood, and this is relevant also for the inverse Leidenfrost effect, especially what I was mentioning about the effect of the temperature of the surface. So now, after this brief introduction or this brief mention to the Leidenfrost effect, I'm going to explain the inverse Leidenfrost effect. So in this case, what we can imagine, as it's called inverse, is that instead of having a flat surface and a drop of liquid, what we will have basically is a solid body which is embedded in a fluid. In this case, with the temperature of the solid has to be high enough to vaporize the surrounding liquid. And at some point, what we observe is that a stable layer of vapor develops around the surface, as we can see here. And because of buoyancy forces, the vapor is transported towards the real stagnation point. These experiments that were published by Balears and co-workers in 2010 are done with a liquid which is called perfluorexane, and it has the particular feature that has a lower heat of vaporization, which is roughly 40 times smaller than that of water. So this phenomenon, which was or they coined the inverse Leidenfrost effect, was also known for many years for the community of heat transfer. There are many situations and industrial applications where we have a solid body that has to be quenched in a liquid, and then there is a layer, a vapor layer that develops around the body, and then this results. People from the heat transfer community were interested in obtaining the control relations for the Nusselt number in order to predict how much or the quantity of heat that is transferred from the body to the liquid. As I said before, here we have one of the key parameters in this problem is the temperature of the surface of the body. When the temperature is not high enough, at some point what we see is that there is a transition from one regime, which is called inverse Leidenfrost regime, where we have a stable vapor layer around the body, to still here the liquid is being vaporized, but what happens is that all the bubble generated are not enough to generate a uniform vapor layer. This regime is called nucleate boiling regime, and is related part on one hand with the temperature of the surface, but also with the latent heat of vaporization of the liquid that we employ. There is another parameter which is relevant for this problem, which is the degree of subcooling of the liquid. Right? The degree of subcooling basically is measured or the difference of the temperature of the liquid to the saturation temperature or the boiling temperature. So the closer the temperature of the liquid is to the boiling point, more energy, let's say, or the heat flux coming from the whole body will be employed to vaporize instead of heating up the liquid. So in all these cases, in the two videos that I have shown before, here and before, the liquid was at rest. But what happens when we allow the sphere to fall? In this case, what we see is that the vapor layer developed around the sphere acts as a thin lubricating layer, let's say, and allows the sphere to fall much faster than in the absence of any vapor layer. These experiments are done with the sphere at an ambient temperature around 25 Celsius. Here, the one in the center of the video is at 110, and this is above the inverse Leidenfrost temperature, which is 180 degrees. So measurements of the terminal velocity in those two cases allow to quantify for perfluoroxane, again, I'm insisting in this, that drug reduction was about a factor of 8, or was reduced by around 85%. As I said before, the liquid employed here for these experiments is relevant. So for water, when water is superheated, very close to the boiling temperature, the drug reduction that was observed was about 75%. In experiments that were performed with water at ambient temperature, no drug reduction was observed, even the spheres were at a very high temperature, and that is related with the thickness of the vapor layer that will result, which is probably is unstable. We can even combine this kind of vapor layers with superhydrophobic coatings. So the effect is illustrated in this video. Here we have a sphere which is not coated with any superhydrophobic treatment, whereas this one it is. So at some point, when the sphere cools down, we have observed the transition that I described before to nucleate boiling. And here, still, because of this superhydrophobic coating, we can observe a stabilization of the vapor layer. Yeah.
What's the typical Reynolds number in those?
So 10 to the 5, more or less. Yeah. Well, I have to say that it's not constant. So I mean, when it's based on the instantaneous velocity that is measured in the experiments. So, but here, when almost the terminal velocity is reached, it's around 10 to the 5. Thank you. So, well, I'm presenting all these experiments just to illustrate the relevance of the phenomenon observed, and here even combining the formation of cavities when the sphere impacts the surface combined with the generation of vapor. We can see here that there is a huge cavity that is kept stable when the sphere is falling. And here, reductions, the drag coefficient was measured, the drag coefficient that was measured was around 0.02 more in the experiments, which is even smaller than the one measured in this configuration. So, the thing is that all the experimental work is very nice, and from that one could try to explain which are the mechanisms that allow to reduce the drag of this sphere. So initial theories that were proposed. First one was okay. There is the sphere behaves as a spherical bubble, let's say. So boundary condition at the interface is like one of a free shear flow, and then the boundary layer around the sphere can be described like in the classical paper of Moore. And when we do that, we observe a rapid increase in the thickness of the boundary layer at 130 degrees, which is the angle that is measured here of the weight, what they measure. But if one takes the paper of Moore and looks at the evolution of the thickness of the boundary layer, but basically what found is that the thickness is around 5 or 6 times the initial thickness of the boundary layer, without any other thing that suggests that the flow is detaching or there is a separation of the flow. Second attempt to explain what's going on is this, the vapor layer basically induces a slip velocity at the interface, which can be modeled or can be treated as with an average slip boundary condition. So for that, one has to introduce another parameter, which is the slip length. And again, this slip length doesn't have to be constant because the dynamics of the vapor layer is not far from being understood, and might play a role or an important role in the flow or in the observations of the experiments. So for us, the mechanisms that were explained were not convincing, and then we decided to describe the problem in a theoretical manner to see what can bring to this what can we can bring to this to understand these experiments. So this sketch here is the configuration that we studied. We have a sphere of radius r at a constant temperature T sub s. So the sphere is stagnant, and we have a free stream of liquid. The velocity of the free stream is u infinity, the temperature is T infinity, and this is the reduced pressure at here at the forward stagnation, how it evolves with this vertical current. So, well, we will have, what we expect to have is a thin layer of vapor that I'm giving, which is corresponds with the green solid lines, separated by the interface by the the interface separates the liquid stream, which is marked with the solid blue lines. So with that, we try to, or we aim to understand which are the mechanisms that really explains the separation of the flow, and then to really understand if the vapor stream plays any role in the results observed in the experiment. So assumptions, we consider axisymmetric flow around the sphere. We restricted ourselves only to water as working fluid, basically because properties of liquid of perfluorexane are well known for the liquid, but there are no data available about there is no data available for the properties of the vapor, so we cannot compare or we cannot employ realistic values for the coefficients of the properties of the vapor. So properties of the liquid will be the density, viscosity, and the temperature of the free stream and the temperature of saturation. The temperature, we assume both for the vapor and for the liquid that the properties are constant, and for the liquid are evaluated at the liquid film temperature, and for the vapor are evaluated at the vapor film temperature. As I said, characteristic Reynolds numbers are of the order of 10 to the 5. So we can employ boundary layer description or boundary layer approximation to describe both streams. So to facilitate the numerical integration of the problem, we employ as characteristic scales those derived from the boundary layer flow around the sphere for the liquid. So the non-dimensional variables that we obtain are here, or the normal coordinate to the wall, the polar velocity for both streams, same for the radial velocity, the reduced pressure, and the temperature of the liquid and that of the vapor. So this scaling was done in a manner that the temperature of the liquid goes to 0 at infinity, and goes to 1 at the interface. And the opposite happens with the temperature of the vapor. It goes to 1 at the wall and to 0 at the interface. So here are the conservation equations for the liquid phase. So we have continuity equation, polar momentum equation, and the energy equation. So the pressure gradient for this flow is that of the outer potential flow around the sphere, and boundary conditions at infinity correspond with the velocity of the free stream and the temperature that of the free stream. This equation has to be integrated from the location of the interface that has to be obtained as part of the solution to infinity. Similarly, we can obtain the conservation equations for the vapor phase. So we have again continuity equation, polar momentum equation, and energy equation. I want to emphasize that here in those two equations there is a prefactor, which is the ratio of densities, which in principle is there is a factor of 10 to the minus 3 in the density ratios, and one would be tempted to drop, let's say, convective terms in both equations. This can be done, and has been done in the past, but the thing is that there is a point when I'm anticipating a bit the results, when the thickness of the vapor layer starts to grow, those two terms, even with this prefactor, become important and cannot be neglected anymore. So, boundary conditions at the wall are no slip boundary condition, and the temperature of the wall at the E equals 0. In this case, the domain of integration of these equations goes to 0 up to the position of the interface. That again has to be determined as part of the solution. Okay, still there is something which is missing that comes from the analysis, the balance of or the conservation equations at the interface. So that provides the jam conditions across the interface, which is the ingredient missing to complete the formulation of the problem. So we have the kinematic boundary condition. We have continuity equation at the interface. Continuity of stresses, or the stresses have to be the same at the interface. And the temperature is equal to the temperature of saturation at the interface. This last equation corresponds to the balance of energy at the interface, and basically illustrates that energy coming from the vapor is employed in, first, heating up the liquid up to the temperature of saturation, and secondly, to generate vapor, which is corresponding to this other term. So overall, we have all the problem set, and the parameters or governing parameters. In principle, once the liquid is chosen, all those two parameters are fixed, rank numbers of both fluids. The Jacob number will depend on the temperature of the surface and the liquid that we employ, and also the Froude number, which appear in the gas phase conservation when we also included the effect of buoyancy in the vapor stream. So there are some other terms that we did not include, and this is because they were not relevant. So in particular, buoyancy forces in the liquid. So if one compares buoyancy in the liquid with the pressure term in the momentum equation, this balance basically says that is equal to the Grashof number divided by the Reynolds number 10 to the square, or the square Reynolds number. The Grashof number in those experiments is about 10 to the 6, and for experiments 10 to the 4 or 10 to the 5, this makes that the buoyancy forces in principle can be neglected. Also, it's important to note that when the liquid is going through along the sphere, pressure is changing because of the of changes in the velocity of the flow. That would make eventually will produce a change also in the temperature of saturation, which is given or controlled by the Clausius-Clapeyron equation. In that case, what we did is try to estimate also variations in the temperature of saturation compared to the temperature of saturation, and we observed that those are of the order of the constant of the gas times the temperature of the saturation at infinity divided by the latent heat of vaporization. For water, this is about 0.08, which also is not is small. And finally, well, surface tension effects. I didn't include that in the balance at the interface, but since it can be, we also estimate that this term is small. So there is something that that is important to know, that when vaporization is produced, there is a radial intake of vapor, and that intake of vapor results in a radial pressure gradient. If this radial pressure gradient becomes important, what can happen or what might happen is that boundary layer approximation cannot be valid anymore, in the sense that the assumption of boundary layer would not be valid. So what we try to do is to compare just by balances at the interface to estimate the radial pressure induced by vaporization. So in the energy equation, I mentioned that we have three terms. First term, which is the heat flux coming from the wall, and that is employed to vaporize and to heat up the liquid. So the biggest or the largest velocities that we are going to observe is when the energy is only employed to vaporize, because let's say that there is a part of the energy that in other cases would go to heat up the liquid, but in this case, if only is employed to vaporize, we will have the largest radial velocities, and that, let's say, is the most restrictive case for this balance. So I will consider only the case in which vaporization, the heat flux is employed only in vaporizing the liquid, which is this balance basically is giving me, this is the heat flux coming from the wall, which is of the order of the energy of vaporization, the energy of the produced or the vapor, the energy of vaporization, of the radial vaporization. From the polar momentum equation, we can compare the pressure gradient with the momentum diffusion, and from continuity equation, we can we have the estimate of the relationship between the radial velocity, the polar velocity of the vapor, and the thickness of the vapor layer. The same balance here can be also employed in the radial momentum equation, and combining all these four balances, we can estimate the ratio of the radial pressure gradient to the polar pressure gradient. So this basically is a upper factor, which in the experiments considered goes roughly from 1 to 2, and divided by the square root of the radius, ensuring that the validity of the validity of the boundary layer approximation. So the formulation that we have derived is valid, as the boundary layer approximation is valid, and we still need one thing more to start the numerical integration. In this case, these are the initial conditions. Initial conditions come from the analysis of the conservation equations in the forward stagnation point. In this case, this can be obtained or can be computed because they admit a self-similar solution for small values of theta. And also, I have to provide a good estimate of the vapor layer thickness. So capital Y, I is the value that we obtain, the position of the interface that we obtain from the numerical calculation of the stagnation point flow, and can be put in physical quantity just by applying this transformation. So this here I'm illustrating a parametric sweep in the x-axis I have the temperature of the sphere that goes from 400 degrees Celsius to 800 Celsius, and the temperature of the liquid. So here what we see is, well, we have basically that two cases also when the Froude number is equal to 1 and when the Froude number when buoyancy is negligible in our case. So in both cases we can see that the thickness of the vapor layer varies, let's say, from 20 to 60 microns, whereas in experiments in quiescent spheres the thickness of the vapor layer that was measured experimentally goes from 50 to 150 microns. It's normal that this thickness is higher because we don't have here the effect of the outer flow that would reduce the thickness of the vapor layer. So now the problem is completely formulated, and we can integrate the conservation equations to understand the resulting flow. So first, I'm going to show how the flow of both streams behaves in two cases. In both cases, buoyancy has been neglected, so it's the limit of Froude tending to infinity. And both cases are very similar in the sense that the surface of the temperature is 500 degrees, and the only difference here and here is the temperature of the liquid. So, as I said before, near the stagnation point flow, there is vaporization of the liquid, which is given by these streamlines that I'm plotting here in green, and this is transported downstream. But I want to now to show these streamlines that are plotted in magenta. These streamlines plotted in magenta at some point reattach the surface. This corresponds to a condensation of vapor. At some point, when the thickness of the vapor layer increases, the liquid, the energy coming from the sphere is only employed to heat up the liquid up to the saturation temperature and cannot produce vapor anymore. The balance of energy imposes, therefore, that vapor has to condensate, and that results also in the injection of fresh liquid here and here. Also, because of the of the pressure gradient of the boundary layer of the outer pressure gradient around the sphere, this pressure gradient for theta larger than 90 degrees becomes negative, and it starts to accelerate the flow. It's not plotted here, but in the inset of both plots, what we can see is that past 90 degrees, a recirculation bubble appears, and this solid black line would correspond with the separation, the separation of both of the part of the fluid or the vapor which is moving forward, and the one that starts or is recirculating. Normally, one would expect that in boundary layer flows, this kind of recirculation cannot be observed. But in this case, as we have this term, the density ratio, that makes smaller the convective part in both the energy equation and in the momentum equation, we are able to capture this recirculating bubble. There is a point here after which the numerical integration does not converge, and computation is stopped. But what we observe here is that because of the acceleration of the flow, the recirculating bubble appears past 90 degrees. There is also another thing that I would like to explain, in this evolution plot that I have here in figure P and D. Here is the polar velocity for the vapor in green in both cases, and for the liquid in blue. The thick dashed line corresponds with the potential, the velocity of the potential flow, and one can observe rapidly that the deviations of velocity from the potential flow are not very large, even close to the interface. So, just to summarize a bit, the transport of vapor downstream is hindered by two factors: the spherical geometry, related with the fact that past 90 degrees also, even the increase of the thickness or the position of the interface is monotonic. At some point, because of the geometry, the area is reduced per unit of streamwise length. We have an adverse pressure gradient beyond 90 degrees, and although there is condensation of vapor, this condensation that would allow more fluid, more vapor to go downstream is not enough to overcome these two effects. So, so that would explain what happens in the experiments. Finally, from an operational point of view, because then this we computed afterwards, I will show some computations related with the separation angle. We define the separation angle as the position where the recirculation bubble starts, because in some cases that can be computed, and in some cases we can compute a bit more downstream, but not in all cases. So operationally we define the separation angle as the position where the bubble is formed. So, well, this slide is just to explain a bit more what I have to summarize what I have explained in the past slides. So heat coming from the wall heats up the liquid up to the temperature of saturation, and the excess of energy vaporizes the liquid. At some point, the increase in the thickness of the vaporization layer reduces the vaporization rate, and as I said before, there is a point where the liquid only can be heated up to the temperature of saturation. The energy, and if it's less than that, the energy comes from condensation of vapor that basically results in the injection of liquid. So, the transport of vapor, as I said before, is hindered by the adverse pressure gradient of the outer potential flow. Reduced area per unit streamwise length due to the geometry of the sphere, and there is the effect of the pressure gradient is even stronger because of the density ratio of the vapor to the liquid. So the result is that the vapor that is trying to move downstream at some point, because of the recirculation bubble, doesn't have enough space, let's say, in terms of continuity equation, and that forces the interface to grow to be able to transport the fluid. So, as I said before, the initiation of the recirculation bubble was captured in the boundary layer formulation because of the small density ratio, and the separation angle was defined as the point where recirculation bubble starts. So, as I said before, one of the explanations that was presented in the literature was that the slip length of there is a slip velocity at the interface that can be computed using or employing a constant slip length. The slip length can be computed from now from the numerical integrations. We have the velocity at the interface. We can compute We can compute also the du over dy at the interface. So with that, we could be able to calculate or to estimate determine the slip length along the sphere. So for the two cases that we consider, I'm showing here in the dashed line the one for the temperature of the liquid at 50 degrees, and the one for the temperature of the liquid at 75 degrees Celsius. What I want this here, what we observe is that for sure that the slip length is not constant downstream, but even here, for the case where the degree of cooling is smaller than in the other case, the slip length is negative, meaning that meaning that we cannot employ this kind of approximations to describe this kind of flows. At some point, it becomes singular and starts to becomes positive. So the proposed mechanism that it behaves like there is a constant slip length is not valid, and the dynamics of the vapor cannot be overruled. So finally, I try to we try to study which is the effect of the buoyancy in the vapor stream. So we can see that for relatively small, well, here we have two cases again for 2 degrees of subcooling for the temperature at infinity corresponding to 50 degrees Celsius, and the case of the right for 75 degrees Celsius. We also consider 3 temperatures. In black corresponds to a sphere which is a temperature of the surface is 600 degrees Celsius. In green 500 and in blue 400. So in both cases, what we observe is that for relatively small values of the Froude number, their delay, the formation of the recirculation bubble is avoided, and basically all the vapor can be transported towards the real stagnation point. This is similar to what is observed in the experiments that I showed at the very beginning of the talk. In that case, the fluid was at rest, but in this case, that would correspond with basically the motion of the vapor controlled by buoyancy rather than by the outer flow. And at some point, this cannot be held anymore, and we start the separation angle starts to decrease until it would reach its asymptotic value for Froude at infinity. So, well, finally, I'm going to show or to present the conclusions of this talk. So, as I said before, previous theories overlooked the dynamics of the vapor in the separation of the flow that was observed. Here we showed that it's really the vapor plays an essential role, and it has to be taken into account for an accurate description of the whole flow. The condensation of vapor is essential at some point and results in the injection of fresh liquid into the liquid stream, but it's not sufficient to overcome or to counterbalance the onset of the recirculation bubble, which is given basically or controlled by the adverse pressure gradient. So, what I explained, the geometry, again, I emphasize that, the geometry of the sphere together with the factor of density ratios increase the effect of the adverse pressure gradient. So, well, future directions, because this work has not been my main research line, but things that one realized when doing this research is that For example, the combination of, in the theory, there is not a theory that describes these giant cavities that are formed afterwards in terms of the combination of the vapor and the entrainment of air that is formed during after the impact, and would require further modeling. Also, to understand, well, to really well understand. Sorry. Asif. Well, I leave it like this. I don't think it's important because I'm finishing. So, boundary layer approximation is a good theory, a good initial attempt to describe what's the dynamics of the vapor, but we still require, or we don't have the theoretical, or we should employ other theoretical tools to describe what happens downstream after the formation of the recirculation valve. So, okay, we have observed or we have reported this recirculation valve, but what happens downstream is still far from being understood. Also, other kind of approximations, like for example, employing more complex numerical methods or direct numerical simulations is unfeasible because the thickness of these vapor layers is very small, and would require other attempts to describe what happens downstream requires another modeling rather than boundary layer theory. And as I emphasized again, with a complete understanding of what we call the inverse Leidenfrost temperature is still missing. As it happens with the Leidenfrost temperature that has been observed, that droplets are steady even when the temperature of the plate is below below the Leidenfrost point. Here it will happen the same. Geometry can also play a role, and there are still things that that really need to be investigated in that, or need to be studied in that direction. So that's all. Thank you very much for your attention.
Thanks very much, Jorge.
Yeah, very nice problems and very nice pieces of work. In the case of an isothermal sphere, the boundary calculation would stop, break down, I don't know, about 110 degrees
Yes.
around. And with a square root singularity in the wall shear,
Yeah.
and also in the displacement go up to
Yeah.
the square root singularity. Are you seeing the square root singularity in the streamlines?
So we didn't compute that. So, but probably it should. I guess that the mechanism is similar. The thing is that I don't know, because in the end the Reynolds number in the, let's say, in the vapor stream, if there are, you could also at some point drop the convective terms in the conservation equations. At some point it becomes like a lubrication problem. So I don't know. Because the liquid basically is, there is no, if you look at what happens to the liquid when you have the recirculation valve in the vapor, nothing happens basically. The liquid basically does not know that something is happening in the vapor stream in terms of singularities. So,
But in your graphs at the end, you showed that streamlines seem to be trying to go.
yeah, but this is because the interface is diverging, not because the liquid is reaching the singularity, or there is a singularity in the numerical calculation in the liquid. So the singularity appears in the vapor stream, and then in principle convective terms, if one makes the asymptotic limit with the density ratio very small, if the solution is something like a wet flow plus aqueous flow in first approximation. So But the interesting thing is that the liquid is basically is not altered by by anything. So and everything is happening in the vapor. And the fact of that you have this recirculation bubble in the vapor at some point is forcing to diverge the interface, but still the liquid keeps let's say without knowing that something is happening there.
So you find this nice solution, which is symmetric. Did you consider any symmetry breaking or stability of the solution?
Well, no, we did not know. So probably, for example, what I was explaining that for large degrees of subcooling, that the thickness of the vapor layer is very small. But here, for example, in these calculations, you obtain a steady solution. So probably if you include all those effects and interfacial the effect of the surface tension and so on, at some point that solution would be unstable and would be related, would help to explain why that is not observed in the experiments, I guess.
In the experiments, they won't have any symmetry breaking observation.
No, it's quite symmetric. Even when you see these experiments for quiescent spheres, you only see these traveling waves, but you don't see any asymmetry. I don't know. Maybe it plays at some point it might play a role, but it's not clear. In principle, in the experiments, everything is like a kind of axis symmetry.
And maybe as a remark, the term is different. Gordillo and Guillou, they have shown that somehow the Leidenfrost temperature, which is a very nice way of for drop on the substrate, could be very dependent on the weather.
Yeah.
Is it something that you can implement in the model somehow?
Well, I guess you could try to do something to include, I don't know, super hydrophobic or something like that. Well, I'm not an expert on that, so I don't know. I don't think it's easy. I haven't said that, but it's more or less related related with the effect of the stabilization that has, for example, in the two videos that I presented, when you don't have the super hydrophobic coating and you have it, even you are still producing less vapor, you will still have a much a thinner vapor layer, which is still stable. So. Yeah.
So in your steady state model, you've got condensation, evaporation. Obviously in the experiment you've got ball detachment at the trailing edge of the sphere. So how in terms of your model do you guarantee for global mass conservation of vapor?
Well, I don't think that can be described with this model, because at some point you have this production of bubbles or whatever. With this kind of distribution, you couldn't do it. So,
but in some sense, are you actually creating artificially high condensation to compensate for the fact that you are not losing vapor by ejecting it out into the wake of the drop into the end?
Well, because in the end, this is an evolution problem, and basically what controls everything is what happens before as you go downstream. So it's true that if you, for example, want to include what the realistic geometry, there should be there has to be information coming, let's say, from the real stagnation point that is not included in this theory.
But you're not controlling the vapor stream at all, no? So you don't have conservation of vapor.
Yeah, exactly.
I wanted to ask something different, but this was related to that. And that is namely because you let your temperatures be varying to realistic values.
Yeah.
What could you also increase that, and maybe then the detachment point would get much closer to the lower end of the sphere.
So yeah, what I did that I haven't shown here, but initially, because when I started to work on this, there were only experiments related to perfluorexane.
Yeah.
Then afterwards, experiments related to water were published, and then the previous result that we had, which was with the surface of the temperature of the surface was 200 degrees, and the temperature of the liquid was 20 degrees. And in that cases, I could observe the onset of the separation around 130 degrees or something, or 120. But the thing is that then when you look at the experiments, they say, okay, this is not valid, so you have to restrict to things that can be observed in the experiments.
Thank you. It's a beautiful work.
Thank you very much.
Do you have another question?
I think that last sentence is interesting. It says a theory that accounts for cavity. It's like, is there any work going on?
Well, it's something that I discussed with the other co-author, but we never get into it, but we did. Because also the latest experiments of these giant cavities that I presented in one of the slides were published when we were writing the manuscript, and we discovered that even that was not was far from being understood. So, well, okay, say, this would be nice, but yeah, it's something that we have discussed. I don't know if we try to, we will be able to do it at some point, but
a different answer problem will alter the potential for it.
yeah, exactly. Yeah.
Hence,
Yeah, it becomes much more complicated.
yeah.
Thank you very much.
Okay, let's thank Jorge again.